refrigerator and heat pump both operate under the same schematic diagram. Okay, three circle which stand for warm environment. Okay, and then low temperature area. Okay, so they are working on the same schematic diagram. But what is the difference? Okay, so for refrigerator, they are focusing on the QL. Okay, the cold temperature. And then for the heat pump, you're focusing on the QH. Okay, which means refrigerator focus on low temperature or low temperature environment. And for the heat pump, you're focusing on the high temperature area. Okay, so next. So this is the equation in case you forget. Okay, so you can put it down again. The COPR would be the desired output, which is the QL, low temperature area, divide by the required input, which is the W net in, or you plug in a socket. Okay, and for COPHP, you're focusing on the QH, the high temperature. And for the input, still the same, W net in. Okay, so I want you to highlight these two, put into your equation list. Okay, everyone, highlight these two, put down in your equation list. Okay, and the same, put down this in case you forget during your thermo, put it down. COPHP equals to COPR plus 1. Circle this up. Important equation. Why I say so? Because there's 1 year, I think 4 to 5 years back, there's one past year question. Okay, so they want you to determine the COPR. But all the topic not related to COPR, they only provide you with COPHP. So remember, they provide you COPHP, you can eventually link it with COPR. Okay, so put it down, important, must remember this. COPHP and COPR, they are linked with each other. Okay, next. Okay, so as we know, the reverse Carnot cycle is the most efficient refrigeration cycle. Okay, so I want you to take note here. So for 1 and 2, this is compressor. So compressor, what you're going to do is deal with the compression. Okay, so 1 to 2, it is compression. So I want you to take note here, compression. So yeah, I will write it down for you as well. So make sure you put it down, compression. Okay, it is a compression process. Okay, so still remember, I always mention they always work in opposite direction. Whenever you're going to have compression, you're going to have expansion. Okay, compression, you're going to have expansion with your turbine. I repeat again, they work in opposite direction, which means compression, opposite would be expansion. So write it down. I give you 10 seconds. Okay, so both of the process you're going to deal with isentropic. Write it down. Isentropic compression, and opposite here would be isentropic expansion. Write it down. So what means by this? Which mean you are going to have your S1 same as S2, and right here would be S3 same as S4. Write it down. So take note. This is important. So this is the reverse Carnot cycle. So what means by reverse? Which means it is anti-clockwise. Okay, write it down. Reverse here stand for the anti-clockwise. I want you to put it down here. Reverse, anti-clockwise. Okay, 10 seconds. Write it down first. I want to make sure you can follow me. Okay, so next, here. we are going to have condenser. So we are going to have the heat rejection. Okay, so here will be heat rejection on top. Okay, whenever you have rejection, then you're going to have addition, or perhaps we know it as the absorption. Okay, so they are the same, absorption. Okay, heat absorption. Write it down. This is the heat absorption. Okay, so remember just now for compression and expansion, you put it down as isentropic. Okay, so remember for heat rejection and heat addition, you're going to put it down isothermal. Okay, isothermal, both. Okay, so for both heat rejection and heat absorption, both must be isothermal. Write it down. Okay, so that's why you can see here S1 same as S2. That's why it is a straight line. Here is the straight line. Okay, and then same goes with your 3 to 4 is also a straight line. Why? Because S3 same as S4. This is the isentropic expansion. Okay, and then isothermal rejection. That's why you can see here T2 same as T3. T2 same as T3 and goes with T1 same as T4. That's why it is a rectangular shape. Okay, move in anti-clockwise directions. Okay, clear everyone? Can I proceed? If yes, write down yes at the chat box. Then I will proceed to the next page. Okay, so yeah, if you think that which part not that clear, just let me know. Okay. Can everyone follow me? Okay, thanks, Izan Hazik. Okay, great. Okay, Lau. Okay, great. So next, so this is the equation, COPR. Okay, so I hope you still remember. In case you forget about it, now circle it out. COPR equals to TL divided by TH minus TL. Circle this up. I repeat again, COPR equals to TL divided by TH minus TL. Or you can put it down 1 divided by TH divided by TL minus 1. So from here, how to become here, you just divide by TL for each atom. Okay, so important, TL divided by TH minus TL. Okay, so next, so this is question. A refrigerator working temperature, evaporator, condenser coil, negative 30 and 32 degrees Celsius. So which one? Okay, negative 30 belongs to TL or TH, everyone? Negative 30. Okay, so negative 30 belongs to your TL. And 32 degrees Celsius belongs to your TH. So let's try it out to solve it together. Okay, so right here, insert here. Okay, so your TL would be negative 30. Okay, so remember, everyone put it down. Change Celsius to Kelvin. Write it down, everyone. Very important. I highlight it. Okay, so make sure you follow. Change the Celsius unit to Kelvin. Why? Because later on when you calculate the COP, it must use Kelvin. Okay, and then your TH equals to 32, same. Okay, you have to change it to Kelvin as well. Okay, so next COP, we have to calculate the maximum COP. So how are we going to do it? COP max equals to TL divided by, which one? Let me check. Okay, TL divided by TH minus TL. So it will be TL divided by TH minus TL. So now you just need to fill it in. COP max equals to TL. TL is negative 30 plus 273 divide by 32 plus 273 minus negative 30 plus 273. So your COP max, you should receiving around 3.92. Everyone try to calculate it whether you're getting 3.92 or not. Okay, you should be getting 3.92 for your COP max, which means this is the maximum COP. Okay, thanks Alia. Okay, so this is the maximum, but is this actual? No. Why? Because they let you know the actual refrigerator only has 0.75 of the maximum. Okay, so right now COP actual only 0.75 of the COP max. Okay, which means indirectly it is 0.7 times with your 3.92. So COP actual is actually equals to 2.94. Try to cross check everyone. 2.94, is that correct? Let's try it out. Check it out. Okay, I give you 30 seconds. Calculate it. Okay, if you manage to get 2.94, just put down a like emoji or times of emoji. Okay. Okay, Irfan get it right. Great. Lau get it right as well. Great, great, great. Okay, so this is the COP actual, but what they want you to do it, they want you to calculate the required power input, which means they want to know your W in. Okay, so still remember you're going to have this equation I just mentioned just now. COP equals to your QL divided by your W in. Okay, so COP you already get it, which is 2.94. Your QL, okay, so your QL, which is 5 here, okay, 5 divide by your W in. So your W in is basically 5 divided by 2.94, which is correct, 1.7 kilowatt. Let's check it out whether you're getting the same value or not. Okay, so you should get 1.7 kilowatt. Okay, so I will say that it's not that difficult actually. Thanks, Irfan. Okay, so next, we're going to proceed with the next page. Okay, so there are three different types of methods of refrigeration. Okay, the first one, it is the non-cyclic. Okay, and the other one is cyclic, and the third one thermoelectric. So the non-cyclic is actually the small scale refrigerations. Sometimes you see it at the lab, workshop, not the bulky one, okay, or sometimes you are easier. Some of them they are usually bring it to the picnic. Okay, picnic, they want to store their beverage cold, so they will just bring the non-cyclic type. Okay, or sometimes like like example, there's a football match. Okay, sometimes the team they will bring along the non-cyclic refrigerations to put down all the drinks or the medicine and etc. Okay, but it depends, not all. Okay, so the common one, the one that you going to shopping mall, the electronic appliances shop, then they are selling, most of them are cyclic. Okay, especially the compression type. Okay, for the cyclic, they divide into two. The vapor compressions and the other one is vapor absorption. Okay, but the most common one, you see like example like Toshiba, Panasonic, okay. So all that belongs to the compression type. Okay, and of course you're going to have the thermoelectric. Okay, but what you need to know, you just need to know you're going to have three classification: non-cyclic, cyclic, and thermoelectric. That's all. It's just a surface one. Okay, why? Because you're going to learn in depth during your final year. There's one subject known as refrigeration. Okay, so that one you're going to learn it in your final year if you choose that elective subject. Okay, but currently what you get to know, just know that you're going to have three different type, and cyclic is the one that commonly used, especially the compression type. Okay, so let me show you. So I think you see this before, everyone, correct? The water dispenser, you can find it at C25, E07 level 1 got it, 03 also got it. Okay, especially the one that you're going to have turn it, the red one, red tap is hot water, blue tap is cold water. So inside there, there's a VCRS inside so that it can serve the cold water to you. Okay, so this is the water dispenser, and then you're going to have your refrigerator. I think most of you at home, you're going to have one unit. Okay, so this one also run on VCRS, or inside your car also got it to keep your car compartment, your passenger seat there cool. Okay, so inside here also got the refrigeration system. Okay, so these are the applications, okay, of the VCRS. Okay, so write it down, everyone. In this chapter, you're going to learn two figure. One is the TS diagram, which is quite common. Okay, and the other one is pH, pressure enthalpy. So these are the unique one. So write it down. pH diagram is important. Okay, and it's moved to the right side. Okay, pH diagram. Okay, so I repeat again. In this topic, two diagram important. One is TS, one is pH diagram. Okay, and remember, always start from right bottom corner. Okay, so let me highlight it for you. Okay, so for this one, what you get to do, this chapter TS and pH diagrams important. Okay, and then what? pH, okay, tend to right side. Okay, which means, can you see that? Move to the right side more. It's not straight, it's not straight up. It's slightly to the right side. Okay, and your number one start from left, right. Start from right bottom. Okay, and it should be goes in anti-clockwise. Okay, so put down this note on this page to help you better later on. Okay, I give you 20 seconds, write it down. Okay, so next. Okay, so just for your information, just now we are going to have compressor and turbine. Okay, so this is for the ideal cycle, but remember, in actual refrigeration cycle, you are not going to have turbine. So remember, you're going to make it with Truther valve. Everyone write it down. Okay, write it down somewhere else. Replace turbine with Truther valve. Okay, so I repeat again. There is no turbine inside your refrigerator system. Okay, only Truther valve. Okay, but whenever you replace the Truther valve to reduce the pressure, there is one issue. Okay, it is refrigerating effect reduced. So I want every one of you write it down whenever you are going to install with Truther valve, the refrigerating effect reduce. So take note. Why I say so, still remember just now we are going to have here 3 to 4 is straight line. Still remember, everyone? Okay, if straight line, then your number 4 would be right here. Okay, so your number 4 would be right here. Okay, can you see that? The 4 to 1 is much more wider. Okay, which means 4 to 1 is the cooling effect. If 4 to 1 big enough, then the refrigerating effect increase. But now whenever you install it with through TEWAF, the 4 to 1 become smaller. Whenever it becomes smaller, then the refrigerating effect reduce. Okay, so I hope it's clear for you. I repeat again, if you use turbine, then it will directly move down. Okay, which means the 4 prime to 1 is big enough. Cooling effect is good. Okay, but in the refrigeration system, you're not going to use turbine. You're going to replace it with true TEWAF. Okay, that's why the refrigerating effect here coming down. Okay, so reduce the refrigerating effect. Okay, clear? So next, we are going to proceed with the next page. That's why remember it is a curved line, a little bit curved and move inward, not outward. Okay, refrigerating effect getting smaller. But is there any way to overcome this? Yes, there are two ways. Okay, so the first way is I will show you later on. Okay, but before that, remember before you enter the compressor inlet, here is mixture. Can you see that? Here is mixture. You're not going to put down mixture to go into your compressor inlet because it's going to interfere the lubrication inside the compressor. Okay, so you have to push the one go here from here to until here, which is your saturated vapor, or better you push it to superheated vapor. So everyone take note, the one here before entering the compressor, it must be dry enough. Okay, so I put it down before enter compressor must be dry. Okay, so everyone take note here, must be dry. Okay, that's why it touches the saturated vapor. In fact, better it push to superheated. Best superheated. Okay, so this is the important criteria. Okay, so next one. So this is one of the approach to eventually increase back your refrigerating effect. Okay, can you see that? The red one. The red one here. Okay, so the red one here, if without undercooling. Okay, without undercooling, your refrigerating effect is only here, red line until the 1. But if you perform the undercooling process, then the 4-1 drop until here. Okay, so now the refrigerating effect increase. So remember, take note, undercooling increase refrigerating effect. I want you to highlight this, important. Undercooling increase the refrigerating effect. Put it down. Okay. So next in this topic, I want you to take note. This topic, for you to calculate the COPR, you are going to use H, or we know it as the enthalpy. So write it down. This chapter, we use H for calculation. Okay, some of the topic we use S, some of the topic we use U. Okay, this topic we use H, enthalpy. Write it down. So where is your QL? QL is H1 minus H4. So where is your W net in? So it would be your H2 minus H1. Okay, so this is quite simple. Okay, so just take note, jot down this. Okay, so how are you going to use that? I will show you next time. Okay, but next, compressor type. Okay, so for the compressor type, I would say that it's more than 3 actually. Okay, later on when you go to final year elective subject, you can see it's more than 3. But now we introduce you 3. Okay, so what you get to know in the final later on, they might ask you to list at least 2 or at least 2 type of compressor. Then you can put it down. One is the reciprocating type, and then you're going to have the centrifugal, and you're going to have the screw type. So these are the 3 in your syllabus, but in actual more than 3. Okay, so for this page, just take note, memorize 2 type of compressor, then that will be good enough. whether you want to make it reciprocating and screw type, or you want to make it centrifugal and screw type, up to you, either two. Okay, so next one, this is the equation. Put down in your equation list first. Okay, because yeah, during our physical class, I will solve the partial question with you. Then you will know, oh, when am I going to use this equation? Okay, or how to use this equation. Okay, so this one later on. Now you just circle it up, equation list, equation list, equation list. Okay, so in fact, it's quite the same with your previous chapter, the compressor chapter. Okay, it's almost the same. Okay, so next. So apart from the undercooling, we still have another approach to increase the cooling effect, which is using the flash chamber. Okay, so flash chamber. So what is flash chamber? Some of them will know it as the vapor liquid separator. So this is another name for flash chamber. They are mean the same thing, same item, just that one, they know it as the flash chamber. Some people know it as the vapor liquid separator. Okay, so how it's going to use? For example, if we reaching here, it moved to the left side. So I will show you another figure. Okay, so it moved to the left. When it moves to the left, then the refrigerating effect increase. Okay, so you can see here, the yellow one is the flash chamber. Okay, if without the flash chamber, it move down here. Can you see that, everyone? I repeat again, if you don't use the flash chamber, then it will directly go for 7, drop down to 4 prime. So 4 prime to 1, the cooling effect is smaller. Okay, but if you use flash chamber, you can see that 4 to 1, the cooling effect is wider. That's why this is another approach, okay, to increase the refrigerating effect. Okay, so still the same. It is in anti-clockwise direction. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is flash chamber. The purpose to increase the refrigerating effect. Okay, so yeah, for today, yeah, I will just stop it here. Okay, but of course you can learn how to sketch because here is important. I will show you during our next physical class how to sketch it, but today you try to sketch it on your own first. Okay, next class I will assist you again how to sketch the pH diagram and the schematic diagram. Okay, so yeah, this one also next class I will show you how to calculate it. Okay, how to use the equation. So is there any question, everyone? If you have any question, you can just stay back or you can unmute yourself later on. Okay, so if not, then I will see you again next week. Okay, I think next Monday is public holiday again. Okay, so I will see you Friday physical class. Okay, so thanks everyone. Bye, Wan Amirul. Bye. Bye,
Thank
Ian.
you, Doctor.
Okay, welcome. Bye bye. See you.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Bye bye.
Thank you, Doctor.
Um,
Thank you, Doctor.
yeah.